Hello everyone, we are Group 7. Today we will present our analysis of the adult census income dataset, demonstrating the importance of data preparation for machine learning. Our presentation covers 7 sections, including introduction and dataset overview, and dataset profiling in the EDA, data cleaning and transformation, bias analysis and mitigation, machine learning validation and conclusion. The contribution of each person is in line with the content of our explanation. We chose the adult census income dataset from the UCI machine learning repository. This dataset contains 32,561 records from the 1994 US Census, with 14 features and 1 target variable. Our task is binary classification, predicting whether an individual's income exceeds 50,000 per year. Our objectives are mainly about demonstrate how data preparation impacts model performance, use only interpretable models, logistic regression and decision tree, focus on explanation and insight, not accuracy chiefly. Let's walk through our EDA. Our dataset has 6 numerical features and 8 categorical features. The target variable is income either above or below 50,000. To be specific, this is column information. The third feature means the final sampling weight, indicating how many individuals in the population each record represents. This is numerical features, descriptive statistics. Capital gain and capital loss have high variance. 75% of the values are not greater than 0. However, the maximum values are all very large numbers. This should be outliers. Looking at the target distribution, we immediately notice a significant class imbalance. About 75% of individuals earn less or equal to 50,000, while only 25% earn more. This 3-to-1 ratio is an important data quality issue, like bias we need to address. Examining our numerical features, we see different distribution patterns. Age follows a roughly normal distribution centered around 38 years. Capital gain and capital loss are extremely right-skewed, with most values at 0. Hours per week clusters around 40, the standard work week. This skewed distribution will require transformation. We identified several data quality issues. About 7% of records have missing values marked as question marks. We have the 3-to-1 class imbalance mentioned earlier. Significant outliers exist in capital features. There's redundancy between education and education norm. They are perfectly correlated, and we found duplicate rows in the dataset. Our correlation analysis shows that education norm has the highest positive correlation with income. Importantly, we don't see strong multicollinearity among numerical features, which is good for our logistic regression model. There's a significant gender gap. Males have much higher rates of high income. Education strongly correlates with income. Higher education, higher earnings. Income peaks in the 45 to 55 age group. These patterns reveal both predictive relationships and potential bias. Now, Chen Qinghe will explain how we cleaned this data.
Hi, I'm Chen Qinghe. I will show you how we did the data cleaning and transformation. First, let's look at the missing values. We found that the question mark was used for missing data. Since these clones only had a few missing parts, we used the mode imputation. This helped us keep all 32,561 records instead of losing 7% of our data by deleting them. Next is outlier detection. We used the IQR method to check features like age and capital gain. Looking at the box plot, we made a clear choice. We kept the outliers in capital gain and loss because they are real financial values. However, for hours per week, we limited the value between 1 and 100 to fix extreme cases. Moving on to the encoding, we use the binary encoding for sex and the target for native country. We put real countries into another group to keep it simple. We also used one-hot encoding for other categories and dropped a first clone to avoid extra overlap in our data. For scaling, we choose standard scaler instead of min-max scaler. The reason is really simple. Standard scaler works better with the outlier in our capital data, making those results more stable. Finally, we did the feature engineering to make our model stronger. We created a capital net clone and used the log transformation. We also put age and hours into simple groups, like middle-aged or full-time. This makes our final model easier to explain and more accurate.
Hello, I'm Xuetao. I will show the bias we found in this dataset and how we deal with it. Let's start with the gender and race bias. The gender bias in this dataset is striking. First, males are twice as represented as females in this dataset, and more importantly, males have a 30.4% rate of earning over $50,000 and compared to just 10.9% for females. And that's nearly a triple times difference in the high income rates. And meanwhile, the race bias is important too. Asian and whites has an over 25% of earning over $50,000, which is much more higher than other races. This isn't just a data issue. It reflects historical society inequalities. Also, the bias of gender is more common. Looking at the intersection of race and gender, we see something important. The gender income gaps persist across all racial groups. In every rule of this heat map, males have higher income than females. This suggests a systemic pattern, not a bias of one of the particular subgroup. So, we explore several mitigation strategies. First, we undersampling the majority group to balance gender representation. And secondly, we use inverse frequency weights during training. And lastly, we split the sample to ensure all demographic income combinations are represented. And for class imbalance, we choose smooth over simple oversamplings because smooth creates cynetic samples than just duplicating existing ones. And this will help the model generalize better. We considered undersampling, but rejected it as it would lose valuable majority class information. We also demonstrate Simpson's paradox, a classical analytic facility, where males have higher overall income rates. When we control for education level, the relationship becomes more nuanced. The overall gap is partly explained by different education distributions between genders. This teaches us always looks deeper than a grid statistics. Another important fallacy is that the correlation is not equal. We found that hours worked correlated with income, but this doesn't mean working more hours causes higher income. Confounders like occupation type and education level affect both values. So we should not only focus on one single pattern. Now, Su Zhiyuan will tell you how did we use this data to train the model.
Hi, I'm Su Zhiyuan. Now let me show you how data proportion actually impacts model performance. We decided a controlled experiment with two approaches. The baseline uses minimi pre-processing, just dropping missing values, basic label encoding, no scaling or class balancing. The improved version uses our full pipeline, mode imputation, one-hot encoding, standard scaler, smooth for class balance, and all engineered features. We trained logistic regression and decision tree on both versions. The results clearly show the value of data proportion. Both models improved across all metrics. Most notably, recall improved significantly, meaning we are much better at identifying high-income individuals. The bar charts show the improved model in green consistently outperforming the baseline in red. The ROC curves confirm this visually. Our improved models, shown as solid lines, consistently outperform the dashed baseline models. AUC increased for both classifiers, proving that proper data proportion leads to better discriminative ability. Feature importance analysis shows what drives our predictions. Relationship and marital status are the top predictors, which makes sense since household structure correlates with income. Capital gain features, education level, age, and hours worked also play important roles. Understanding these help explain our model's decisions. To summarize, small effectively addressed class imbalance, feature engineering ended valuable predictive signals, but the key insight is this: data preparation quality matters more than the model complexity. Simple models with clean data outperform complex models with messy data. Now let's wrap up with our key takeaways. We found several important issues in this dataset: 7% missing values, 3-to-1 class imbalance, and significant gender bias where males were 3 times more likely to earn high income. We also demonstrated Simpson's paradox, showing how aggregate static tests can mislead us. Most importantly, proper data preparation significantly improved our models. Our data preparation made a real difference. Mode imitation preserved all 32,000 records. Small improved recall for the minority class. Feature engineering added valuable predictive signals, and proper encoding and scaling helped our models learn more effectively. Together, these steps transformed a messy dataset into one our simple models could handle well. Our key lesson is data preparation matters more than model selection. Bias exists in real data, and we must identify and mitigate it. Pitfalls like Simpson's paradox remind us to dig deeper than surface statistics. Building authentic AI requires considering fairness at every step. This project reinforced that data governance is fundamental to responsible AI. The goal isn't just accuracy, but ensuring our outcomes are fair, interactable, and trustworthy. Thank you for your attention. Thank you.